Okay, so this is Introduction to Statistical Learning, Chapter 7, and we're on the applied questions, question 9. So we have a lot of things to do, and what we're going to do is look at the Boston data set, and we're going to predict DIS, which is the weighted mean of distances to 5 Boston employment centers, and NOx, which is nitrogen oxides concentration per part in 10 million. Okay. So again, we're predicting DIS as a function of NOx. Okay, and we're going to use, in parts A through C, we're going to use polynomial regression, and then in parts D through F, we're going to use a spline. Okay, so the first thing, well, really the first thing that you need to do is to make sure that you, if you're going to run this in Colab, that you've gone to runtime, change runtime type, and that you're in R here. Okay, I think it defaults to Python. Oh, and now we have Julia. Yeah. Okay. So then we're going to load the ISLR2 package. So we install, load, and now we get the data Boston set, and I'm just calling the data set D. Okay, even though the data set is called Boston. Okay, so for part A, we're going to use the poly function to fit a cubic, which means third degree polynomial. Let me just clear this. And then, so we're going to use a third degree polynomial to predict NOx using DIS. Wait, did I say that wrong the first time? Have I done this all backwards? I hope I haven't done this all backwards. Predict NOx with DIS. Okay, that's what I've done. I think I said the opposite earlier. Okay. And report the regression outputs. Okay, so we have a model for polynomial. Okay, so I'm using NOx, predicting it with DIS, and I'm wrapping DIS in this poly function up to degree 3. And I'm going to get the summary output here, and we'll also plot it. And so to plot it, well, here, let me just run this. So let's look at the summary output first, and then we'll look at the plot. Well, I mean, I don't know really what to say about the summary output here. Okay, but for the first degree term, you know, this is the statistics for that, and for the second and the third degree polynomial. But really, we want to see how all of these things kind of mash together to fit the data. So this is the fit to the data. So of course, the data is in the black dots, and then our cubic polynomial is this red thing right here. Okay. You know what? Just for interest, let's run this out a little ways. So okay, so what I've done here is I've created a bunch of values for DIS, for distance, and then I'm going to predict using the model that we just fit, but now using my made-up values for distance, and then I'm going to plot it. Okay, and then I'll get then I'm going to get my lines here. Okay, so we run that, and let's see here. I want to go way out, so I want to go to x lam equals c. Sorry for doing this on the fly here, but let's go out to 24. Okay, let me pause this. Okay, so we're back in business here. And I guess what I wanted to show was kind of what happens to the extremities of, polynomial regression, right? It extrapolates far beyond the data, and it will often do things that you would not expect to happen, right? So here, our last data point, kind of looks like it asymptotes, towards some value below 0.5. And then the model will just happily extrapolate that it then just plummets. Okay, and this is just a function of, this is just a byproduct of constraining our function to be a cubic polynomial, right? This is just the shape of a cubic polynomial. So that's what I wanted to do that for. So yeah, I guess I'll just leave it like that. All right. And so now we're going to fit many different polynomials, say from degree 1 to 10. And we're going to use we're going to try to pick the best one, reporting the residual sum of squares. And in part, so that's part B, and then in part C, we're going to pick, the best, the quote-unquote best, the best one using cross-validation or some other approach. And I'm going to use AIC just because it's simpler and the concept is good enough for here. Okay. So let me get rid of that here for a second. Okay, so we're basically going to do what we just did up here, but now I'm going to go through 10 different degrees of freedom for the polynomial, right? So P polynomial, I have degree of 1, 2, 3 all the way up to 10. And then I'm going to store the RSS and the AIC values in these vectors that I've created up here. And just to give some parity to what we just did, let me copy and paste what I did up here for the limits, just so we can see the the extrapolated behavior of these different polynomials and see maybe how crazy they get. So that should go right here, I believe. Okay, hope that works. And I think I multiplied this by like 2, right? Okay. Okay. So let's run this here. So again, all we're doing is creating the same model that we did above, but for different polynomial degrees, and then we're going to find the best one here. Okay, and I've broken something, of course. Okay, give me a second. Sorry. Okay, now we're back online. Okay, so this is very interesting. Okay, so here's our plot right here, and so you see that the data ends right here. So let's first just look at how my cat is playing my guitar. Look at how the tail behaviors here all behave, with these extrapolated polynomials, right? They start to do some wild things, right? So anyway, but let me go back now and well, I guess we don't have to. Okay, so what we were supposed to do then is to look at the fit of all of these polynomials. We could zoom in, and I'll let you play with the code to zoom in, or just pull out one after the other. But in the legend here, I've taken each degree polynomial, found its RSS and the AIC value, and then just found the lowest AIC value and put that as the title here. Okay, and I think that kind of meets everything that we're supposed to do for parts B and C. Okay, now for parts D, E, F, we do basically the same things, but now using our splines. Okay, and so in part D right here, we're supposed to fit 4 degrees of freedom, a spline with 4 degrees of freedom. And because if I do all, so I'm going to kind of envelop that with part E, where we're supposed to fit a range of different degrees of freedom here, okay, 4 being among them. So I'm just going to kind of politely skip this part and just do it as part of the next part of the problem. And then I'm going to use again AIC to kind of find the best one. So we need to make sure that we install and load the splines package here. And you can look at the code here, and I encourage you to do so. Just kind of see how this is done. But it's not that dissimilar from what we did here for the polynomial regression, right? But now I'm defining different degrees of freedom for the splines, and I'm using a spline as my model rather than a polynomial. Okay, and of course the thing I want to do is to change the limits here and here, so we can see what the tail behaviors are like, just because I guess it's kind of interesting now, and we've gone so far, and why stop now? So here, I'll put it there. That should do it, I think. Yeah. Okay, and of course I've broken something. Okay, give me a second. Okay, so just upon some reflection, I mean, nothing is broken. This is just a warning that the that you get with splines if you're extrapolating beyond. So it's telling you that you're extrapolating, and that's maybe cause some problems. But let's look at this guy right here. Okay. Okay, so we have all of our different fits, and the one with the lowest AIC values happens to be number 10 here. So that's this gray dotted line here, right here. So there's that. Now, what else is okay? So we probably should not use either of these methods to extrapolate. But if extrapolation was important, you know, when we look at these, you know, there's only a few behaviors that maybe make sense, and that's maybe these ones that kind of asymptote here, which would be it looks like maybe 9 and 5. Okay. Anyway, I'm not making any value judgments about what the best thing to do here is. You probably should not extrapolate, but again, you can use the code and play with the code to zoom in or pull out, you know, particular models and, you know, see all the little nuances and differences between